Welcome you all. In this session, we are going to discuss how to select the number of poles for decimation. Factors that are affecting the number of poles in decimation. The first factor is frequency. As we are aware, frequency F is equal to 120 F by P. And here the frequency and number of poles, they are inversely proportional. As the number of poles increases, the frequency of induced EMF increase. Core loss of armature increases and therefore efficiency get decreased. So if the frequency increased, the efficiency get decreases. So a minimum frequency is maintained. Second factor, weight of iron used for yolk. Since the flux carried out by yolk is approximately 5 by 2 and the total flux is 5T, which is equal to P5, is a constant. For the given machine, the flux density in the yolk By is equal to 5 by 2 divided by the cross-sectional area of yolk. So it is 5T divided by 2 PAY, which is proportional to 1 by P into AY. Therefore, the density is inversely proportional to P. And from this statement, you can also say it is clear that AY is directly inversely proportional to number of poles, as BY is almost constant. Thus, the number of poles increase AY and hence the weight of iron used get reduced. Second is weight of iron used for armature core. Since the flux carried out by armature core is 5 by 2, eddy current loss in armature core is proportional to B square into F square. So it is directly stated that it is inversely proportional to the area and it is independent to number of poles. On other hand, since hysteresis loss in the armature core is proportional to B power 1.6 into F, it is stated that the armature core area AC is inversely proportional to poles. Decreases as the number of poles increases for a given hysteresis loss. Thus, the weight of iron used in armature core reduces as the number of poles increases. The next parameter is weight of overhang copper. For a given active length of coil, overhang is directly proportional to pole pitch. Pi d by P goes on reducing as the number of poles increases. As the overhang length reduces, the weight of inactive copper used in the hang also reduced. So the active length of coil is AF, it's shown in figure, and ABC or ADE is the inactive part of coil. So pole pitch in case of tau 4 is the pole pitch for pole machine and tau 6 is the pole pitch for 6 pole machine. So in the diagram they have mentioned tau 6 and tau 4, they are nothing but pole pitch for 6 pole machine and 4 pole machine. So the next parameter is the armature reaction. Since the flux produced by armature phi A is ATA by pole divided by reluctance, and the armature ampere turns ATA per pole is equal to IAZ divided by 2AP is proportional to 1 by P. They are inversely proportional to poles. And phi A reduce as the number of poles increases. This in turn reduce the effect of armature reaction. Overall diameter. When the number of poles is less, ATA by pole, and hence the flux produced by the armature is more, this reduces the useful flux in armature gap. In order to maintain a constant value of air gap flux, flux produced by the field or the field armature turns must be increased. This calls for more field coil turns, and since a size of coil defined by the depth of coil df and height of coil hf increases. In order that the temperature rise of coil is not more, depth of field coil is generally restricted. Therefore, the height of field coil increase as the size of field coil or the number of turns in the coil increases. As the pole height is proportional to the field coil height of poles, and hence the overall diameter of machine increases with increase in height of coil. Obviously, as the number of poles increases, height of pole and hence the overall dimension of machine decreases. So, if the number of poles increases, the height of pole get reduced and the overall dimension of machine is also reduced. That is, the diameter get reduces. So, here they have stored for a 2-pole machine and a 4-pole machine, we can compare. See, for a 2-pole machine, the diameter is high as compared to the 4-pole machine. See, for the 4-pole machine, it is less. So, the next parameter is the length of commutatum. Since each brush arm collects the current from every 2 parallel paths, current per brush arm is equal to 2Ia by A, and the cross sectional area of brush per arm AB is equal to 2Ia by A del B, which is again equal to 2Ia by P del B, that is inversely proportional to poles. Reduces the number of poles get increases, as AB is equal to TB, WB and NB, TB thickness, WB width and NB number of tubes. Okay. If TB is generally a constant, the commutator point of view, WB and NB reduced as AB reduces, and hence the length of commutator LC reduced as AB reduces. So, here WB is width, TB is thickness and NB is number of brush per spindle. The next parameter is flashover. As if suppose the number of poles increased and the voltage between the segments increases, because of this increased voltage, a carbon dust collected in space where the mica is uncut, chance of arcing between the commutator increase. So, if the poles get increases, the flashover, so the possibility of flashover get increases. The arc between the segments in turn may bridge the positive and negative brushes, leading to dead short circuit. So, the number of poles must be reduced or it must be minimized. So, the next parameter is the labor charge. As the number of poles increases, the cost of labor increase as more number of poles are to be assembled. More field coils are to be wounded, placed on the poles, insulation and so interconnections, etc. So, the work as well as complexity increases. Again, if you see the labor charge get increased, it's all because the number of poles getting increased. So, once the number of poles get increased, automatically the number of coils get increased. So, the assembling charge, the wounding charge, those things get increased. Thank you.